Welcome to this explainer. Okay, if you've ever driven down a completely pitch-black highway at 2 in the morning, you already know exactly why today's topic is absolutely crucial. We're looking at a wildly innovative project presented at the AOP 2026 conference. It's called the Distributed Adaptive Road Lighting System, and it literally promises to revolutionize how we drive at night. So let's dive right into the incredible engineering behind this and see how this so-called predictive light wave actually works.
Section 1, the Nighttime Lighting Dilemma. Okay, let's dive into this. Before we can really appreciate the genius of this new technology, we have to understand the massive headache city planners currently face with empty roads at night. Right now, managing that lighting is a huge compromise. On one hand, you've got scheduled dimming. Sure, it saves a few bucks on energy, but it's fundamentally unsafe. It completely ignores whether a vehicle is actually there or not, which creates these super dangerous dark zones for drivers. On the other hand, there's continuous lighting. Keeping the lights blasting at 100% all night long? I mean, that's incredibly wasteful, creating a maximum energy drain on roads that are completely empty. So neither option is really a winner.
Now, you might be thinking, well, what about simple motion sensors? Don't those exist? Actually, the researchers highlight a really critical point here. High-speed traffic requires anticipation, not just detection. Purely reactive sensors might work perfectly fine for a pedestrian walking path, but at highway speeds, they switch on way too late. By the time a basic sensor detects your car flying by at 120 kilometers an hour, you're already passing the light. We need a system that can essentially see into the future.
Section 2, the predictive light wave. Let's see how they'd actually solve this.
So here is the researchers' brilliant solution. I want you to imagine driving down a dark highway, and a literal red carpet of light just smoothly rolls out ahead of your car, right when you need it, and then cleanly fades away behind you. To create that red carpet effect, the system relies on one core metric, estimated time of arrival, or ETA. Simply put, ETA is the calculated time until a detected vehicle reaches the next luminaire, or streetlight, in the chain. This calculation right here, this is the secret sauce. It lays the total groundwork for how these smart streetlights know exactly when to wake up before you even arrive.
Let's take a micro journey down the road and see the 6-step predictive light wave principle in action. Step 1 is detection. The first node spots your car. Step 2, it calculates that ETA we just talked about. Step 3 is UDP propagation. This is basically the streetlight whispering your speed data to the next streetlight down the road. Then we hit Step 4, which is where the magic happens, predictive fade-in. The next light turns on before you even get there. Step 5 is vehicle passage, where you cruise safely under full bright illumination. And finally, Step 6 is return to baseline, where the light quietly dims back down to 10% to save energy. And this brilliantly illustrates the exact timeline of that process. Notice how Node 1 detects the vehicle at the exact 1-second mark. It instantly fires off the speed and data to Node 2. Now, look at what Node 2 does at the 869 millisecond mark. It schedules its light up for a smooth 2-second fade, starting a full 500 milliseconds before the vehicle physically arrives. It doesn't wait to actually see the car, it completely trusts the math and lights the way in advance.
Section 3, Edge-Based System Architecture. Let's lift the hood on this tech.
We've seen the theory in action, but now we need to look at the actual physical hardware that makes this predictive wave possible on a normal street pole. Every single luminaire in this setup is a smart edge node. Inside, you have an ESP32 dual-core microcontroller that's acting as the brain. For eyes, it's rocking a 24 GHz FMCW mmWave radar, which is capable of instantly detecting both distance and velocity. For our mouth and ears, it uses Wi-Fi and UDP unicast communication to talk to its neighbors. And finally, it controls the actual LED lights using standard DALI-style dimming control. It's basically a fully self-contained smart device right on the pole.
Now, notice how the edge computing concept works in reality here. Look at those blue arrows pointing between the ESP32 boxes. That's the Wi-Fi UDP unicast we just mentioned. Node 1 is talking directly to Node 2, and Node 2 is talking directly to Node 3. The huge takeaway here? They are not sending data all the way up to some slow, centralized cloud server just to ask for permission to turn on the lights. They communicate entirely locally, peer-to-peer.
And that brings us to the absolutely fundamental rule of the entire system. Critical, real-time decisions remain at the edge. By keeping all the processing power right there on the street pole, the system totally avoids communication bottlenecks or, unexpected internet outages. This guarantees the lightning-fast speed required for highway traffic, plus the fail-safe autonomy that drivers literally depend on for their lives. I really want to emphasize that this isn't just some theoretical concept gathering dust in a white paper. In this laboratory validation from the ISEL campus in Lisbon, these ESP32 nodes are actively running a highly complex finite-state machine.
The researchers have actually built and tested these controllers in real life, ensuring that the radar acquisition and the tricky state transitions between things like idle, light on, and safe mode work perfectly under lab conditions.
Section 4. Energy savings and results. Let's look at the hard numbers.
This is where the rubber meets the road. We get to look at the hard data to validate the actual environmental and economic impact of this system. To prove this works at a massive scale, the system was evaluated using a custom traffic event simulator. And they didn't just guess how cars drive either. The researchers fed the simulator with real hourly traffic profiles taken straight from the city of Lisbon. They injected these real-world traffic events natively into the nodes via UDP to see exactly how the embedded code would handle genuine, randomized, messy highway traffic patterns all throughout the night. And the performance metrics? Absolutely incredible. The node-to-node predictive propagation time, which is the time it takes for one streetlight to calculate the ETA and tell the next streetlight to turn on, has a local median reaction time of just 4 milliseconds. 4! That is lightning fast. It ensures that even the fastest-moving vehicles on the road will never, ever outrun that predictive light wave.
So, the crucial point here, the real headline from the AOP 2026 conference, is the sheer scale of the energy savings. When tested against typical continuous lighting scenarios during low-load nighttime traffic, this adaptive system achieved a staggering 81.2% energy savings. You are literally getting over an 80% reduction in power usage without ever once sacrificing the safety and visibility of a continuously lit road. It's a total game changer.
To really visualize that impact, just look at the red bar on the left. That represents traditional continuous lighting running at 100%, burning through a massive 4.50 kilowatt-hours over the test period. Now look at the green bar right next to it, labeled C4 Adaptive. The predictive system used a mere 0.85 kilowatt-hours. That visual difference is just massive, and it totally proves that smart edge perception fundamentally flips the energy equation on its head.
So where are we actually going to put this into practice? Well, the researchers outlined the best deployment contexts to maximize its impact. First up, low and medium AADT, that's annual average daily traffic, highway segments. Second, rural and interurban roads. And third, access roads with long, empty road intervals. Basically, any place where traffic is discontinuous at night, meaning the road just sits completely empty for long stretches, but when a car finally does come along, it needs full, safe visibility instantly.
And this brings us to a really fascinating conclusion for this explainer. As this decentralized, radar-equipped edge technology inevitably graduates from laboratory testing and hits real roads for field validation, we really have to ask, is the era of the dangerous, dark highway finally over? By giving our infrastructure the ability to actually predict our arrival and light the way just in time, we might just make nighttime driving safer and radically greener than ever before. Thank you so much for joining me to explore this brilliant research.